Hey everyone, so we're going to go over the LHospitals Rule. So question 1, use LHospitals Rule to evaluate the limit as x goes to 0 of 14x cubed minus 6x squared plus sine of 9x, all divided by x times x minus 1. Alright, so the first thing we need to ask is, can we actually solve this limit without using LHospitals Rule? Is LHospitals Rule even applicable here? And I guess we should go over what LHospitals Rule actually says. It basically says if we have a limit, right, of some form. Let's say we have the limit as x goes to 0 of f of x. LHospitals Rule states that if this equals some indeterminate form, such as 0 over 0 or infinity over infinity, and so on and so forth, then we can take the first derivative of the top and the first derivative of the bottom and divide them, and this could give us some the proper limit, basically. So what we're going to do here is we're going to ask, can we take this limit? So let's figure out what this equals. The limit as x goes to 0 of 14x cubed minus 6x squared plus sine of x, or sine of 9x, over x times x minus 1. So what is this? Well, we can see that 14x cubed as x goes to 0, so this term goes to 0. 6x squared, this term goes to 0. And sine of 9x, this is the same as sine of 0. What is sine of 0? Sine of 0 is 0. So this is 0 over 0 times x minus 1, or 0 times 0 minus 1, I guess. This also goes to 0, so we end up with 0 over 0. Since we have an indeterminate form, we can use LHospitals Rule to evaluate this limit. So what are we going to do? Well, we're going to take the derivative of the top first. Let's say x goes to 0 of, what's the derivative of the top? Well, the derivative of 14x cubed is the same as 42x squared minus the derivative of 6x squared is 12x. And then sine of 9x, this is a simple chain rule application, so we have the derivative of the inside times the derivative of the outside function. So let's see, sine goes to cosine, cosine goes to negative sine, so this would be plus 9 cosine of 9x, right? And this would be all over, well, what's this? Let's FOIL this out. So we have x times x minus 1. This is equivalent to just distributing x squared minus x. So the derivative of this would be 2x minus 1. And so we just need to calculate the limit as x goes to 0 of this function. Well, what does this equal? 42x squared goes to 0, right? Minus 12x goes to 0. Plus, well, 9 cosine of 9x. This term right here would just be 1. This would just go to 1. So it would become 9. 9 times 1 over, what is this? This is 2 times x goes to 0, so that's simply 0 minus 1, so we just have a negative 1. Or this can all simplify down to simply negative 9. So this would be our value of the limit evaluated using LHospitals Rule. All right, moving on to question 2, we're going to evaluate the indefinite integral of 6z cubed minus 8z plus 16. I'm going to have to remember to say z and not x here. I'm so used to that. So basically, we're going to perform the opposite of derivative. We're going to take the antiderivative of each of these terms. This is a fairly simple one to solve because we just have z terms tacked on. We don't have division. We don't have a chain kind of operation. We simply have just z terms on every component. So we don't have to worry about, for instance, something like cosine of 8z taking the antiderivative of this. We don't have to worry about that, right? So this should be fairly simple. Let's see. So I'll just rewrite this. 6z cubed minus 8z plus 16 dz. Okay, so first of all, let's worry about this term. What is the antiderivative of 6z cubed? Well, we just have to remember what it means to take the antiderivative. The antiderivative is simply going to be this term raised to the power plus 1, and then we're going to divide everything by the new power. So for 6z cubed, the antiderivative would look like 6z to the 4, right? Raise the power by 1, divided by whatever the new power is, in this case 4, okay? Minus, let's move on to this term. We have 8z, so this would be 8z squared, because this is a 1 term above it, divided by the new power of 2. And then for 16, we just need to remember that this is equivalent to writing 16z to the 0 power. So all we need to do is just raise that power by 1, so plus 16z. And if we wanted to, we could divide this by 1, but since anything divided by 1 is simply itself, we don't need to worry about that. And now we just need to remember that because there is an infinite number of derivatives that fit this these criteria, we need to add on a plus c. Essentially, this is equivalent to saying we have this curve right here, but this curve is the same curve whether we shift it down or shift it up, for instance. It's the same curve no matter where it's shifted, and so the plus c is just taking that into account. Now to simplify, all we need to do is find what terms go into what. So 6 and 4 are both divisible by 2, so we can say this is equivalent to 3z to the 4 divided by 2 minus 8 and 2 are both divisible by 2, so this is just 4z squared. And then plus 16, that's just plus 16z plus c. And if we look over here, we can see that solution 3 fits what we're looking for. So that's our answer. All right, our final question. Determine the critical points of the function f of x is equal to 9x cubed plus 6x squared minus 12x plus 4. So we need to just remember what the critical points are. And this is just a definitional thing. So we have that critical points where critical points are where the derivative of the function either equals 0 or does not exist. So for instance, if we have the graph of an absolute value function, a critical point would be here, because the derivative does not exist where the 90-degree turn is in the function, basically where it has the point. Likewise, if we have another graph, something like this, an upside down parabola, a critical point would be right here, because this is where the derivative is equal to 0, where the graph flattens out, right? Sorry, that's supposed to be flat. I'm very bad at drawing. So these are examples of critical points. So for our function here, we're just going to search for those critical points. We're going to try and find where the function where the derivative either doesn't exist or where it equals 0. And so to start, we're going to have to take the derivative, of course. So f prime of x is equal to, because all of these are simple, just polynomial terms, we can simply use the power rule. So just dropping down the exponent and multiplying by it. 9 times 3 is 27. So this is 27x squared plus 6 times 2 is 12. So plus 12x minus 12. And then this term is just a constant term goes to 0, so we just cross that off. We can write a plus 0 if we wanted to here, but this is equivalent. So this is our derivative. Now we're going to find where the derivative either does not exist or equals 0. So for this, because we have a simple parabola, right? It's going to look something like this. Right, sort of shifted down 12 notches. In fact, I think it'll be more like this. It'll be shifted to the left a little bit, I believe. Feel free to check that if you want to. But because it's just a smooth curve, there isn't going to be a place where the derivative does not exist. It basically exists at all points on the graph. So we only really need to worry about this place right here, where the derivative equals 0. Now, to find that, or the multiple places it could be, we are going to use the quadratic equation. We could try to factor this if we really wanted to, but I mean, this is going to be a pain. And we can see that by looking at some of the answers. I mean, do you really want to try and factor this somehow with these kinds of results? So the quadratic equation states that the roots of a function are going to be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, where these terms here all correspond to the coefficients on a standard quadratic polynomial. So ax squared plus bx plus c. These would be the coefficients. So for this kind of function, we have coefficients of a here. Oh, that looks like I'm dividing. That's not good. So a, b, and c. So all we need to do is just substitute these into this equation. So we can rewrite this as x is equal to negative b, which is negative 12, plus or minus the square root of b squared, which is 12 squared. I know that as 144, minus 4 times a, which is 27, times c, which is 12, all over 2a, which is 2 times 27. So if we go through the process of simplifying, this becomes negative 12 plus or minus the square root of everything in here simplifies down to 1200 or 1440 rather. And this is over 54, I believe. So we've got this. Now, we always want to look for ways to simplify our radicals. This radical can be rewritten as the square root of 36 times the square root of 40. And this is valuable to us because we know what the square root of 36 is, right? It's just 6. So this becomes 6 times the square root of 40. And so this whole expression can just be rewritten as negative 12 plus or minus 6 square root 40 all over 54. And now we can look for values that we can simplify out from all of these expressions. So rewriting it, we see that we can divide out a 2 from all of these terms. And so this can be rewritten simply as negative 6 plus or minus 3 square root 40 all over 27. I don't believe it can simplify any further. Actually, it can, right? We can divide out a 3 from all these terms. 3 times 9 is 27. So actually we can simplify it even further, dividing out a 3. So we get negative 3 plus or minus square root 40 over 9. And so this is actually, these are our two expressions. Basically we've got, this implies that x is equal to negative 3 plus square root 40 over 9. And also x is equal to negative 3 minus square root 40 over 9. So I've just realized there's actually an error in my math up here. One of these, this was meant to be the right solution, but I used the incorrect term for the bottom here. I multiplied incorrectly. So, you know, sometimes people get things wrong. I'll have to go back into the problem set and redo this a little bit. But these are our solutions. So negative 3 plus square root 40 over 9 and negative 3 minus square root 40 over 9. So that's the end of our problem set for today. Thank you very much for watching, and have a good one.